Hello everyone. So in today's video we'll discuss about state variable method. This is a continuation of the previous lecture. So this is lecture 2 in state variable method. So in the last lecture we discussed about how to obtain the state model for differential equations, electrical system and for mechanical systems. In today's video we are going to discuss about if transfer function is given, for the given transfer function for that particular system, how to obtain the state model. So in this video I have given two different examples. So those two different examples we'll discuss. Now the first example, the transfer function y of s by u of s, it is given, which is equivalent to s square plus 7s plus 2 divided by s cube plus 9s square plus 26s plus 24. So for this given transfer function, obtain state model. Now I am going to represent the given transfer function in the form of block diagram. So here where y of s it is considered as output, u of s it is input. So in the block diagram I am going to split this given transfer function into two different blocks. So for this blocks, the input it is taken as u of s, the output it is taken as y of s. The first block consists only the denominator polynomial. So 1 divided by s cube plus 9s square plus 26s plus 24. The second block, it consists only the numerator polynomial, which is s square plus 7s plus 2. As per the block diagram reduction technique, when two blocks are there in the cascade, so to combine those two blocks into a single block, we have to multiply those two blocks individual gain values. When we multiply these two blocks, we will obtain the given transfer function. Now, first let me take only the first block and obtain the state equation. So in the first block, the in between branch, for this branch the output I will consider as C of s. So for this block the output it is C of s, the input it is u of s. So where output by input it is transfer function, which it is whatever it is there in this block. C of s by u of s it is 1 by s cube plus 9s square plus 26s plus 24. Now just by doing cross multiplication, u of s into 1 which is equivalent to s cube C of s, 9s square C of s plus 26s C of s plus 24 C of s. 24 it is constant value, so 24 into C of s. Now the equation what we obtain, u of s, this equation is there in the Laplace transform domain, frequency domain. Now if I have to convert this s domain into time domain, then u of s becomes u of t, s cube C of s, it is d cube by dt cube. So d cube C of t by dt cube, I can return it as c triple dot of t. Here second term 9s square C of s, which can be written as 9 d square C of t by dt square. So 9 c double dot of t. The third term plus 26 s C of s. So 26 d C of t by dt, which can be represented as 26 c dot of t plus 24 C of s can be represented as 24 C of t. So let me consider this as equation 1. Now, so in time domain we have written now u of t equation, input equation. So here this is there in the differential equation. So in this differential equation, the order of this equation it is 3. So the state variables are equivalent to order of the system. So number of state variables are equivalent to 3. So now we have to consider three state variables, x1 of t, x2 of t, x3 of t. So x1 of t, it is c of t, x2 of t, c dot of t, x3 of t, c double dot of t. That is how we have taken the state variables x1 of t, c of t, x2 of t, c dot t, x3 of t, c double dot of t. So when we write c dot of t, which is equivalent to x1 dot of t. When we write c double dot, which is equivalent to x2 dot or x1 double dot. So for x3 dot, if we write, x3 dot will be c triple dot of t. Now let us substitute these above state variables into the equation 1. So u of t, how it becomes? U of t as it is, in one equation only one x dot should come. So in this equation u of t, c triple dot it is can be replaced by x3 dot. C triple dot can be replaced by x3 dot plus 9 c double dot can be replaced by x3 of t. C dot can be replaced by x2 of t, 26 x2 of t plus 24 c of t can be replaced by x1 of t, 24 x1 of t. That is what written over here. U of t x3 dot of t plus 9 x3 of t plus 26 x2 of t plus 24 x1 of t. Now only x3 dot of t, let us keep it in the left hand side. Let us bring all other terms to the right hand side. And from the previous equation, x2 dot of t is x3 of t, x1 dot of t is x2 of t. So as per state model, we have to take state equation as x dot of t, which is equivalent to a u of t, a x of t plus b u of t. So where x dot of t, it represents x1 dot, x2 dot and x3 dot. x3 dot we obtained it. x2 dot is x3 of t, x1 dot is x2 of t. x2 dot, x3 dot we obtain, x2 dot is x3 of t, x1 dot of t is x2 of t. Now from these three equations, whatever we have written for x1 dot, x2 dot and x3 dot, let us write the state equation. First equation, x1 dot of t, 0 x1 plus 1 x2 plus 0 x3, 0 x1, 1 x2 plus 0 x3 plus u of t is 0, so 0 u of t. x2 of t, only x3 of t is there. So 0 x1 of t, 0 x2 of t plus 1 x3 of t plus 0 u of t. And x3 dot of t, x1 coefficient minus 24, x2 coefficient minus 26, x3 coefficient minus 9 plus 1 u of t. So this it is called as state equation. Now we have to write it for output equation. So this we obtain it from the state equation, we obtain it from the first block. Now in the second block, when we see the second block, here we can write a transfer function only for the second block, where y of s by c of s is equivalent to s square plus 7s plus 2. So with respect to that, now output equation, where y of s is by s of s is equal, y of s by s of s is equivalent to s square plus 7s plus 2. So just do the cross multiplication. Y of s is s square c of s plus 7s c of s plus 2 c of s. This is Laplace transformed equation. Let us obtain into the time domain y of t s square, so c double dot of t, single s, so c dot of t, 2 c of s is 2 c of t. Where in this y of t equation, we will replace the state variables, where y of t, which is equivalent to c double dot, it is x3 of t, c dot it is x2 of t, c of t it is x1 of t. So output equation, y of t it is, so x1 of t coefficient it is 2, 2 x1 of t, 7 x2 of t, 1 x3 of t, 1 x3 of t plus in this equation there is no u of t. So 0 u of t. So this is how we have to obtain state model when we get transfer function. So in this first example we discussed the transfer function where in the given transfer function we had numerator polynomial and denominator polynomial. The given transfer function, if we have numerator polynomial and denominator polynomial, this is how we have to obtain the state model. Now we'll see the next example. We'll see the next example where in this given question the transfer function has in the numerator constant value and denominator polynomial. If this kind of transfer functions are given, how we have to obtain the state model? Obtain state model for this given transfer function. Then, so here the given transfer function y of s by u of s, it is 24 divided by s cube plus 9s square plus 26s plus 24. So when we have this kind of transfer function, first step we have to cross multiply this. When we do the cross multiplication, we will obtain s cube y of s plus 9s square y of s plus 26s y of s plus 24 y of s, which is equivalent to 24 u of s. Here the obtained equation, it is there in the Laplace transformed equation, the form of Laplace transformed equation. Convert this S domain equation into time domain equation. So convert this S domain equation into time domain equation where s cube is there. So d cube y of t by dt cube plus 9 d square y of t by dt square plus 26 single s, so single derivative 26 dy of t by dt plus 24 y of t, which is equivalent to 24 u of t. Let us consider this as equation 1. Here, whenever we obtain differential equation, so we have to first check the order of the obtained differential equation. So here the order of the differential equation is 3. So number of state variables are equivalent to order of the differential equation, order of the system. 3 state variables we have to assign: x1 of t, x2 of t and x3 of t. For the differential equation, how do we assign the state variable? From this side we will start. x1 of t is y of t, x2 of t is dy of t by dt, x3 of t is d square y of t by dt square. That is how we have written. x1 of t is y of t, x2 of t is dy by dt, which is equal to x1 dot of t, x3 of t is d square y of t by dt square, which is equal to y double dot of t, which is equal to x2 dot of t. Now, in this equation 1, replace all the differential, all the state variables, and here one more state thing, x3 dot will be d cube y of t by dt cube. So substitute all the above state variables in the equation 1. When we substitute, we will obtain x3 dot of t, which is equivalent, x3 dot of t plus 9 x3 of t plus 26 x2 of t plus 24 x1 of t, which is equivalent to 24 u of t. When we replace the state variables in the obtained differential equation, only one x dot of t we have to replace. All other things to be replaced by normal state variables. Now, only x3 dot of t, put it in the left hand side, bring all other terms to the right hand side. So that is what written over here. So from the previous assumption, x2 dot is x3 of t, x1 dot of t it is x2 of t. On output equation y of t it is x1 of t. So the state model will be from this x1 dot of t, left side x2 dot of t, x3 dot of t. So first we will say x1 dot of t, only x2 term. So 0, 1, 0, x1, x2, x3 plus 0 u of t. 0 x1 of t, 1 x2 of t, 0 x1 of t plus 1 x2 of t plus 0 x3 of t plus 0 u of t. Now x2 dot of t is only x3 of t. x2 dot of t is 0 x1 of t plus 0 x2 of t plus 1 x3 of t plus 0 u of t. x3 dot of t, x1 coefficient is minus 24, x2 coefficient minus 26, x3 coefficient minus 9, u of t coefficient 24. x3 dot of t minus 24 x1 of t plus minus 26 x2 of t minus 9 x3 of t plus 24 u of t. This is state equation. Now output equation y of t, it is x1 of t. So output equation y of t, it is only x1 of t. So 1 x1 of t plus 0 x2 of t plus 0 x3 of t plus 0 u of t. So together the state equation and output equation, it is called as state model. So thank you. So in this video it's very clear that if transfer function is given, how to obtain state equation and output equation. Thank you.